esteemed honors physics student. So I want to spend a little bit of time going over the test, and then I'll stop the video, and then I'll make another one for the review for the final. So usually, like when I try and write a test, I usually put the first question as like kind of a confidence builder. Here's an easy question. So question number one is what units of all forms of energy measured in? Okay? And remember that work equals force times distance. That was the whole basis of it, right? Which is also a change in energy, right? And forces in newtons and distances in meters. So you get like Newton meters, okay? That's it, okay? Now, you can also realize that that represents joules, right? Because that's what all forms of energy are measured in. So Newton meters and joules are the exact same thing, okay? So literally, I put number one there as a gift, and some of you still missed it, and I just wanted to go like scream and pull my hair out. But anyway, so a lot of that was a little bit frustrating. So the other question that was missed quite a bit, and this is what worries me going into the final. If you remember, it's question number 17 about, you're told a gaseous system has 2100 joules of heat energy removed. So here's the system, right? Okay. So we're going to take out 2100 joules of energy. Now, and this is what's going to happen on the final. I'm just going to give you the numbers. You have to know what to do with them. But I'm going to tell you, I'm going to remove 2100 joules of energy. So I'm going to put this thing like in an ice bath, okay? I'm going to take energy out of this thing. Then it says, while 900 joules of work is done by the gas, okay? And I put in big bold letters the word by the gas. So what that means is that this volume is going to get bigger. It's going to take some of that energy that's inside of it, that these molecules have, and it's going to push against the machine. So, because you have an atmospheric pressure that's trying to keep it down. So, that would be like this system. So here's the system, right? I'm going to take energy out of it, but at the same time, the volume is going to be getting bigger, okay? So, and again, I just tell you 900 joules. I don't tell you it's positive or negative, but I just tell you that's how much work is done by the gas. So I'm going to take energy out. I'm going to take thermal energy out. So that's a negative 2100. Then at the same time, it's going to do work. So that's also going to cost it 900 joules of energy. So those two together are negative 3000 joules. So if you look at what's going to happen on the volume, work is done by the gas, so the volume is increasing. Then it says, is the temperature increasing or decreasing? Well, look, I've got a negative Q and I've got a negative W. So I'm taking energy out of the system because it's cooling down, and it's doing work to make that volume get bigger. So those two together are going to be sapping energy out of this thing, okay? So the temperature is going to decrease. Then it says, is the pressure increasing or decreasing? Well, look, you have two things that are happening. You're taking Skittles away from Timmy, okay, so if you go with the Timmy analogy, Skittles are being taken away, and at the same time, it's costing it energy because of the fact that it's making this volume get bigger. So you're going to have fewer collisions. So in terms of Timmy, you're taking Skittles away, and you're making the room get bigger. That's going to make that pressure drop like a rock. You have both things working against you in terms of pressure. You're taking away Skittles, and you're increasing the volume. Now, if I said, hey, I'm going to dump energy into it, and I'm going to do work on the system, then that would make the pressure go up immensely, because then I would be adding thermal energy into it, so I would be giving Timmy Skittles, and I would be making the volume get smaller, so you'd have more collisions that way. So thermodynamics is all about the preposition. All about the preposition. That previous question, and again, I promise you, you're going to see one like this, okay? This is the one where you had the steel plate, and you have your buoyant force acting up, you have your tension acting up, and you have your gravitational force acting down. So you wanted to find the tension. Well, the tension is going to be the difference between your Fg and your buoyant force, okay? Well, Fg is just the mass of the steel times g, okay? You all have done that calculation since the very first lab you were all in here. Now, the buoyant force is where you ran into trouble, because that's going to be rho v g. That is the density. In this situation, it was salt water. So that density is 1,025 kilograms per cubic meter. Okay, it's slightly more dense than fresh water. This is why it's easier to float in fresh water. Now, that volume has to be the volume that is submerged. Well, you don't know the volume that's submerged, but I gave you the mass. And you had to realize that the density of the steel is equal to the mass of the steel divided by V. So you can look at that chart, you can find the density of steel, you know the mass of the steel, solve for the volume. So that volume is going to be the mass of the steel divided by the density, and that volume worked out to be like 0.274 cubic meters. There you go. So make sure, if you haven't thought about that, make sure you get that one. Now, here's the question that was missed without doubt the most. And that was question number 20, where you had a cylinder and it was going to roll down the hill. So here's the idea, okay? And again, this is a big picture. So you have UG up there at the top. Now, because this thing is going to roll down the hill, okay? Jack and Jill went up the hill, okay? They rolled down the hill. So that means they have kinetic energy and rotational kinetic energy. And a lot of you said, oh, I'm just going to set that equal to KT. No, you can't. It's moving and it's rolling. So you've got to go, oh, well, that UG is mgh. That's going to be 1/2 mv squared. And that's going to be 1/2 I omega squared. Okay, you have the two types of energy. Now, you can find the moment of inertia, that's 1/2 mr squared. You don't know omega, but here's the whole key to this. You've got to come in here and go, oh, well, V equals R omega, so omega equals V over R. So this becomes 1/2 mv squared plus 1/2 mr squared times V squared over R squared. So the R squared is going to cancel out. These m's are all going to cancel out, and the short version is that you get, if you combine everything, you get GH equals 3/4 V squared, and then you go V equals the square root of 4/3 GH, okay? And again, here's the bigger idea, that you only have potential energy at the top, and then it's going to change into rotational and translational kinetic energy on the way down. Anyway, so there's going to be that. Speaking of energy, there was that last problem where the spring is going to shoot that marble out, and you're told that you have 0.0527 joules of energy stored in the spring. And this thing is going to swing out here like this. And I got some weird answers. I got answers over like 180 degrees. I think the biggest answer I got was 192 degrees. So this thing is going to swing all the way up and around like that. So this is a situation, it's like, look at your answer and see if it makes sense. So all you had to do was take that 0.0527 joules. So that's how much potential energy it's going to have up here, which is going to be mgh. So your h is 0.336 meters. And you go h equals L times 1 minus cosine theta. So there's your h. And a lot of you got to this point and then your algebra just failed you, okay, because you had to get theta by itself. So if you solve for theta, that's going to be the inverse cosine of 1 minus h over L. So if you divide by L and then subtract 1, but that gets you negative cosine, and then you don't want a negative, so you multiply everything by -1, that's what you end up with. And then your angle works out to be like 40 degrees. So anyway, and then one other one I'll talk about, then I'll stop this. It was question number 19 where you had a graph, and we talked about this the day before the test, okay? So here's your pressure, here's your volume. So this is going to start at some temperature initial, and it's going to end up at so this initial temperature and that final temperature is going to be the same, because PV equals nRT. So these two values are the same. So that means you're going to have the same change in temperature, which means you're going to have the same delta U. Okay, so delta U is going to be the same. So that's why A is correct, because they're going to have the same change in temperature. Okay. Now the work is different. Now also remember that delta U equals Q plus W. Well, this lower one has a much smaller area than the upper one does. So the upper one has a much bigger work, so it's going to have a much smaller value of Q. The lower one is going to have a smaller value of W, so it's going to have a bigger value of Q to get that same change in energy. So there's that. Okay, I'm going to shut this down, and then I'm going to make another one specifically talking about the final. So I'll be back.